Hi, and welcome back to Integrated Science. I'm Miss Sparks, and today we are going to talk about the fundamentals that make up a mechanical wave. So previously we started talking about the idea of just the different types of waves that we can have between mechanical and electromagnetic. And then we broke our mechanical waves down into longitudinal as well as transverse. And so we're going to take a look at how we can measure how much energy is moving through each one of those different types of waves. So do get out a sheet of paper and some notes as we kind of go back and talk about a few things. So previously we talked about the crest and the trough and our wavelength, and today we're going to add to that just a little bit. So the first thing we're going to discuss is amplitude. And amplitude is how much energy is moving through a system. And so in our definition for waves, amplitude is the maximum distance that a particle of wave medium vibrates from their resting point. The greater the wave's amplitude, the more energy it has. And so if I were to draw a line through this right here, I'm going to go back here actually and let you write it down. So imagine that I have a wave that is drawn. Actually, here's the best example, is think about you are hooked up to a heart monitor. So at the hospital, and you hear beep, beep, beep. That is picking up some of the information that is energy that is being distributed through your body. It's picking up an amplitude. If you have a high heart rate, it might be beep, 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 beep. And if you have a really low one, it might be beep, beep, really slow. And so let's say that, God forbid, that, well, let's just pretend that you've been watching like Grey's Anatomy or something like that, and someone flatlines and you hear, that means no more energy has been moving through their system. Their amplitude is at zero. It's at resting point. The heart is not beating anymore. So you want to hear that beep, beep, beep. Otherwise, then you're at rest, and you don't want to be at rest. So you want that maximum distance of the particle. So amplitude is that peak that it gets to, and that peak that it gets to on the heart rate. Doot, 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 doot. So the greater the amplitude, the more energy it is moving through a system. Same thing with, like, if you've ever seen like one of those maybe like a movie where there's an earthquake and you're looking at the Richter scale and they've got the seismograph and it's like ticking really fast. The higher those peaks are, the stronger the earthquake is that's moving through the system. So one of the big things that we'll talk about with amplitude is that we can figure out some other pieces of information with wavelength. And wavelength is very similar to our equation speed that we have talked about. So wavelength is the distance from any point on a wave to the identical point on the next wave. Crest to crest. That's the easiest way I say to think about it. So you'll find one crest of the wave, you'll find the other crest, and then you're going to measure the distance. And that's going to give us our wavelength. We can also find wavelength by taking the wave speed and dividing it by frequency. And I'll show you how to do this. They all kind of connect once you find one. But you can also just measure the wavelength. It's from crest to crest. Another unit of measure for a wave is called a period. And a period is just the time it takes to complete one cycle. Meaning, so here's our rest point again, this line here, and here's our wave in the green. Wavelength from crest to crest. Amplitude is the height from rest point to crest. And our period is starting at the rest point, going up into one crest, going down to one trough, and then back to the rest point. That's our time period, our period of time. How long does it take to get from one crest through one trough back to the beginning point? And so once again, wavelength, crest to crest, amplitude, rest point up to crest, and then our period is from rest point to crest to trough, back to rest point. A period is very important because it kind of tells us how fast a wave is moving. So how long does it take to complete one cycle? And that cycle means from rest to crest to trough back to the rest point. And so we normally measure that with our equation, period. P was taken, so in physics we use T, capital T, not a small, that'd be time, equals 1 second divided by frequency. So the higher the frequency of the wave, the lower the period, meaning that the faster it's moving, the lower period time, meaning the shorter amount of time it's going to take because it's moving really, really fast. And so the last thing that we're really going to focus in on is the frequency of the wave, which is how many times or how fast it is moving in relationship to a fixed point. Excuse me. So the frequency of a wave is the number of wavelengths that pass a fixed point each second. We measure frequency in hertz, Hz. And to find frequency, we are going to use the equation right here. Frequency equals the velocity of a wavelength divided by the velocity of the wave divided by the wavelength. And so really sometimes you can just look at how a wave is drawn, and if its crests are really close together, that's going to represent a high frequency wave. And if the crests are really far apart, that's going to represent a very low frequency wave. And we'll kind of talk about what that looks like as we kind of move through here. So the last thing I want to kind of touch on is our wave speed. And so this is very similar to what we did back when we were talking about Newton's 3 laws of motion. Speed equals distance divided by time. Same thing here. Wave speed equals distance from crest to crest divided by the frequency, how fast it's moving in regards to time. So wave speed is related to wavelength and frequency and the period by using the equation frequency times wavelength. And so what we're looking at is from crest to crest, and then how fast is it moving from one cycle to the next. And so we're going to use all that information to kind of figure out what that looks like, how the behaviors are, kind of identify where the amplitude is and everything else with a wave, so that we can just look at one and be able to say that's a high frequency wave, that's a low frequency wave. So therefore that means it has high speed or low speed. So we're just going to get used to looking at observations so that we can give qualitative information. So hopefully this was helpful, and we're now going to practice these.